So I'm going to talk about the trig in Maths 1M. But in order to do that, I just want to have a look at our seminar that we gave on understanding a maths object. Because this is really the framework for understanding anything, and it'll work fine for trig functions. So we need to ask ourselves, what is it? What can we say about it? What can I do to it? And what can I do with it? And really with trig functions, there are only a small number of things that were under those headings. So the what is it is really what the definitions of what the functions are. And included in that is trying to understand the fact that we're using radians to define them. What can we say about it? We can say a few things about them. We can find their derivatives, we can find their amplitudes, and we can draw graphs. What can we do to them? Well, we can do these awesome trig identity things to them. And what can we do with them? Well, we can model other stuff with them, which you don't do so much. So that's what we're going to work on. But for the rest of it, it'll be on the document camera. The notes of which I will... Okay. Lovely. I will put anything I write here on the Maths Learning Centre webpage afterwards as a PDF, where afterwards means that's probably tomorrow morning. All right. Okay. So, well, let's see. Well, there's two basic trig functions. There's your sine and your cos, and there's also tan. And the original definitions of them are to do with triangles. That's what trigonometry means. Trig means triangle, and ometry means measurement, so they're for measuring triangles. And the basic definition is that if you had a triangle, a right-angled triangle, that had an angle here, and this was A, B and C, then sine theta would be opposite over hypotenuse, and cos theta would be adjacent over hypotenuse, and tan theta would be opposite over adjacent. So this was opposite over hypotenuse, this was adjacent over hypotenuse, and this was opposite over adjacent. And the purpose of sine and cos and tan in the original use of them was to try and describe the relationship between the sides of triangles of certain shapes. So your angle theta over here completely describes the total shape of this triangle, and there'll be a whole lot of different triangles of different sizes, but no matter what size they are, if you do this division, it'll always come out to the same answer if you start with the same angle. And sine and cos and tan were trying to record what that number worked out to, so that if you had a triangle that was bigger, you could still figure out what the other sides were. So that's what they started with. But in Maths 1M, we start to redefine them based on points on a unit circle. So this is what you may have seen in year 9 or 10 or at some point in the distant past. We're going to redefine them to mean something else, but it's still important to know what these are. Okay, cool. So what we're actually going to do is our new definition. Our new definition is that we draw a circle of radius 1. Like that. And then included in this new definition is a new definition of angle as well. So instead of measuring angles in degrees, we're going to measure angles in how far it takes to go around the circle. So we get an angle is actually now a distance around the edge of that circle, starting at the point 1 on the x-axis. That's my angle there. I'm going to call x instead of theta so I don't get confused. And I might make it just a little longer so that you can see the sine and the cos easier. And then starting at 1 and going anti-clockwise will create a point on this circle And the height at that point is sine, and the distance, the x-coordinate is cos. So this is cos x here, and this is sine x here. So that's pretty much it. So sine x is the y-coordinate. Oh crap, really should have used theta instead of x. You can see that these seminars are not, I only told you about it on Friday, which basically means I make it up on the day. So sine of theta is the y-coordinate and cos of theta is the x-coordinate of that point on the unit circle. And that's our new definition of what both theta and sine theta and cos theta are. So that means that we're able to define what sine and cos theta mean for any angle, no matter how many times around the circle we go, because we just say, oh, you want 470 degrees, just go around often enough and you'll get to a point and you can figure out what the x and y coordinate are, and that's what sine and cos work out to be. Tan theta is the slope of that line. That goes from the origin to your point. It's also another distance in your picture as well, which is why it's called tan. Tan theta is actually, if you draw a tangent at that point, it's how far this is to from there to the x-axis. That's what tan is as well. Okay, so that's our new definition. And in order for this whole definition to work, we have to define theta as not an angle in degrees, but a distance around the edge of that circle. Because the reason we do that is so that our differentiation works when we get up to differentiation. Okay. So the first thing that you need to know is what sine and cos and tan are for the basic angles. Okay, so sine and cos and tan are the basic angles. So your basic angles are pi on 2, which is 90 degrees, and pi on 4, which is 45 degrees, pi on 3, which is 60 degrees, and pi on 6, which is 30 degrees. So I remember these by drawing a triangle. This triangle has one here and one here, and because of Pythagoras' theorem it has root 2 here. And it's a square that's been cut in half, basically. And this angle here is 45 degrees, which is the same as pi on 4 radians. When I convert from degrees to radians, I think pi is 180 degrees, so pi on 4 must be 180 divided by 4, which is 45 degrees. And that tells me that sine, being the opposite over the hypotenuse, is 1 on root 2, because it's opposite over hypotenuse. And cos of pi on 4 is adjacent over hypotenuse, and tan of pi on 4 is opposite over adjacent, which is 1. That's how I remember them. When I did my first year maths exams, it's the first thing I wrote down in reading time when I got into my exam. And then your other angles, your two other basic angles, come from this triangle. So the big triangle is an equilateral triangle. All the three edges of this side and this side and this side are all the same. And I've sliced it in half down the centre. And being an equilateral triangle, this is 60 degrees here. So that's pi on 3 there. And that's pi on 6 there. And the way I mark this triangle out is I make the longest side 2. And then this is half of that, so it's 1. So in my head, it's easier for me to remember 1, 2, root 3 on that picture than it is to remember the actual angles, the actual answers to all of them. If it's easier for you to just remember what they are, go for it, and don't let the computer, the pictures confuse you. But that's saying that for pi on 3, sine is opposite over hypotenuse, which is root 3 on 2. Cos of pi on 3 is adjacent over hypotenuse, which is 1 on 2. and tan of pi on 3 is opposite over adjacent, which is root 3. And sine of pi on 6 is opposite over hypotenuse, which is 1 on 2. Cos of pi on 6 is adjacent over hypotenuse, which is root 3 on 2. And tan of pi on 6 is opposite over adjacent, which is 1 on root 3. They're your basic angles, and they're the sorts of angles that are going to come up in an exam because they don't necessarily expect you to be able to know any of the others. And then that means that they can say give exact answers, which means it can all be in terms of root 3 and root 2 somewhere. Okay? Right. Now, if we want to figure out sine and cos and tan of any other angle at all, we should be able to bring it back to angles that do fit into a right-angled triangle. So, big or negative angles is using your unit circle. And it's easier just to do an example of this. So, find sine of 7 pi on 3. Okay, so you may have noticed when you did complex numbers recently that the reasoning that's required for finding a complex number it's in polar form and converting it to ordinary form is the same reasoning as used for finding sine and cos and tan of stuff. So the reasoning, what I do is I do this. So first draw my picture of my unit circle and I figure out where 7 pi on 3 is, which I have a feeling is actually going to be pi on 3. So, and the way I do that is I think about what I would get to get a whole multiple of pi. So I actually convert my 7 pi on 3 to a mixed number. So 7/3, without the pi, 7/3, well, that would be 2 1/3 pi, which means it's got 2 pi and 1/3 of pi. Which is actually all the way, I need a different colour, all the way around here, and then another 1/3 of pi, which is actually like here. So what that means is that I've ended up getting back to where I started if it was just pi on 3. So it's the same as sine of pi on 3, which was root 3 on 2. So that one was a little easier than I was hoping for, but I'll do a different one in a second. The key is that when we figure out angles, sine and cos and tan of angles that are bigger than 90 degrees, we want to find out where the nearest multiple of pi is. So the easiest way of doing that is to write it as, you know, a mixed number so that you can find the whole number of multiples of pi and the other bit. So what if we did tan of 5 pi on 4. Okay? Well, I need to think of that as a mixed number. What is 5 pi on 4? Well, 5 quarters. Well, 4 quarters would be 1 whole, so it's actually tan of 1 1/4 times pi. So that's telling me that here is 1 lot of pi, and there's another 1/4 of pi. So we are in fact here, at that point there. And we want to know how far away from the nearest multiple of pi we are. Well, the nearest multiple of pi is actually there, so we're wanting to look at this angle just here, that pi on 4. So it's actually going to, the way that this works is it's going to come out to the same as tan of pi on 4, like 1/4 of pi, except we just need to check to see if it's plus or minus. And the way that I was taught is to go, they're all positive there, sine, tan, cos. Tan is positive down here, so it's actually going to be equal to the same as tan of pi and 4, which is 1. Tan is positive here. You can also check in your head if tan is positive because the slope of this line is positive because it's going up, and tan is the slope of the line. So we need one that's not going to come out to a positive answer, so you can see how that works. I won't do tan, let's do cos. Let's do a pi on 6, hey? Pi on 6. Okay, so that's already 5/6 is already, as a mixed number, it's already less than pi, so we don't have to convert it to a mixed number to do this. And we're going to go 5/6 of pi, so that's almost all the way to here, but not quite. And the bit that's left, the nearest multiple of pi is here. So that's 1/6 of pi left over. So it's going to be the same as cos of pi on 6. But we just have to check whether it's going to be plus or minus. So let's see. Okay, this says that sine is the positive one over here, so cos must be negative. And cos of pi on 6, according to my diagram, was root 3 on 2. Okay? You can also, you don't have to do the ASTC thing. You can just look and say cos is the x-coordinate, and over on this side, the x-coordinates are all negative, so I know it has to be a minus. So, and I spent, quite some time helping people do this in the Maths Drop-In Centre several months ago, because it can be a bit alien if you've never done it before. Me and your lecturers, do it all the time, and me in particular, because I help people with their maths all the time. Your lecturer only teaches 1M, once a year and does it in the lecture. And it's something that's so familiar to them that they forget that it's hard. So don't be embarrassed to ask about anything that seems easy, especially at this time of year when you want to fill in those gaps. Okay, now, normally what we could do with a function, okay, so this is all well and good, this is lovely, but at the moment it doesn't feel like it's a function. When we think of a function, we think of a graph. And we think about being able to solve functions. So you did logs and exponentials and you were able to have like e to the x equals 4 and you could solve that equation. So when you're doing functions, the things that you can do with them is you can graph them and you can solve equations with them. And solving equations with trig functions is hard because lots of different angles will give you the same answer. Okay, I need to do one more before I move on. Because it only just occurred to me. Cos of 7 pi on 2. I haven't told you what cos of pi on 2 is in my lovely diagram up above, because I can get it directly from my unit circle. So, let's think about that. As a mixed number, that's 3.5. Lots of pi. So here we go, 1 pi, 2 pi, 3 pi, and half a pi. So that gives me this point just here. And cos of an angle is the x-coordinate of the point you end up with, and this is on the y-axis. It lines up with 0 on the x-axis, so it's 0. And you can get that directly from the diagram. So what I would do when I got into my exam is I'd draw my two triangles, and I would also draw the unit circle with the x-coordinates and y-coordinates of those points and the ASTC, and that would be everything I needed to figure out trig of stuff. Okay, so when we have functions, the next thing we want to do is maybe solve equations. So far we've got a handle on what happens when you put an angle into the function and what number comes out? Okay, so you put angles in, numbers come out. That's what the function does. It's a machine that things go in and stuff comes out. We want to do it backwards. We want to say, well, this number came out, what angle went in? Let's put it, just make it hard for ourselves. Solve sine 2x is equal to root 3 on 2. Okay, so there's two parts to this. First, they haven't indicated to me whether there's any restriction on what the x is allowed to be. So that means that there's actually going to be infinitely many answers, because every time I come around the circle again, I'm going to get another angle that gives me the same answer. So there's going to be like some unknown integer in it. It's good to know that you're going to have something like that. And the answer is an angle, because we want to put an angle in here that comes out to that. And our angle is going to be written in radians, because that's how mathematicians prefer it. And the first step is to think, well, what angle could go there to produce root 3 on 2? And, well, we have to think, maybe it's one of our classic angles. And we could look that up and see, let's see, aha. Sine of pi on 3 is root 3 on 2. So pi on 3 is one of the options. It might not be the only option, but it'll be a good start. I'm going to draw a diagram of it. So pi on 3, about there, is one of the options. But there should be other angles that produce the same answer as well. I should be able to go over here where sine is still positive, and there'll be another one there. Okay? Because sine is the y coordinate, that's at the same height as this one, so it's giving me the same answer. So that angle there is 2 pi on 3. Okay? And then sine's negative down here, so I'm not going to get a plus root 3 on 2. And then when I come around another 2 pi from both of them, I'll get another 2 answers, and I'll get another 2 when I come around another 2 pi, another 2 when I come around another 2 pi. So it looks like what we're going to get is that 2x is either going to be root pi on 3, which was our first one, plus some multiple of 2 pi. So I put the number k there. It could be anything. You could use m, you could use n, just as long as it's just a letter. And that's saying that no matter how many times I go around another 2 pi, I'll get the same answer for sine. Or I could get 2 pi on 3 as well. And there are all the options for anything that could be equal to what's in that gap there. So if that was just sine x or sine theta, I'd be done. That'd be my answer. But it's 2x, so I'm going to have to divide by 2 as well. And technically, at the point when I introduce the k, I should say for k being some integer. So that symbol means in, and that's the fancy z for integers. So that means that my x, which I've run out of space for, so same deal as always, I deal with the outside. When I'm solving equations, I pull off the stuff on the outside, and then I pull off the next thing. I'm going to have to pull off the 2, so I'm going to have to divide everything by 2. So I'm going to get pi on 6 plus pi k, or divide that by 2, pi on 3 plus pi k. Yay. So I just divided each thing everywhere by 2, and that's my final answer. So the steps that I went through were to think of what angle could go in this spot to produce this answer, and think of all the possible angles. So I found the one here in the first quadrant first, and then I found the next one. Anything else that could happen from that, and then I went round 2 pi to get the other ones. And that's solving equations involving sine and cos. Sometimes they tell you that you actually want to solve the equation, so something like this. Solve, cos, maybe tan. Tan of theta is, let's go 1. for theta between minus pi and pi, say. So often they'll give it to you from 0 to 2 pi, or from minus pi to pi. If they're really creative, they might go from pi to 3 pi. They could do anything. Okay, so but they'll usually give you a range that includes 2 whole pi's. So same deal's going to happen. First, I'm going to try and figure out what angle could go here to produce the answer 1, and pi on 4 is a pretty good choice. So I could get my pi on 4. And that would give me the right answer. And then let's think about what else in this circle does it. So I need it to be, I need it to be positive as well. So I'll come down here and I'll also get that one as well. And now I need to interpret these as angles between minus pi and plus pi. So the only way to deal with a range that involves both negatives and positives is to split it into the negative bit and the positive bit. So the positive bit goes that way, and the negative bit goes that way, because negative angles are measured clockwise. So the point in this top half is pi on 4, so that's fine. The point in this bottom half goes this way, so it's going to be minus something, and that's pi on 4 down here as well. That's the same angle, so that must be 3/4. That's 1/4 of pi. That must be 3/4 of pi, so minus 3 pi on 4. And that's it. There are 2 answers. That's solving equations. So far we've figured out how to put numbers in and put angles in and what numbers come out. And now we've figured out how to do it the opposite way. So, well, if this came out, what angle went in? And in general, there's almost always 2 answers. And the next thing would be to draw graphs of them. How are we going for time? Okay, doing well. So we could draw some graphs. And your graphs of trig functions do not have the unit circle in them, because that's not what I'm trying to achieve here. When I draw my graph, what I'm trying to achieve is down here, these are my angles, and on the y-axis, these are my outcomes. So I'm thinking if I choose an angle, and these would be all the anti-clockwise angles, and these are all the clockwise angles, and what I need to do, if I was drawing sine, for example, is that if I had a particular point here, I would draw that angle in radians on my unit circle, and then I would find the height of that point, which is what sine is. Sine is the y-coordinate, and I would draw that height here, and that would be the height that I get. And I would have to do that for every point. That's how the diagram is created. But of course, we don't need to do that, because you're supposed to just know what they look like. You traditionally use T, don't you, in Maths 1M? Yeah. You'll find in Maths 1A they usually use S. So, just warning you. So, sine, this would be my t-axis, this is my y-axis. Sine passes through the origin, because sine of 0 is 0. And you mark it out in multiples of pi on 2, because every pi on 2 the same numbers repeat, but in a different order. And it goes the same opposite direction, etc. And sine is positive between 0 and pi on 2. That's that first thing where we have sine being positive in that first quadrant. And it tends to go up, and then it gets to 1, and then it comes down again, and then it goes down, and then it comes up again. And it goes in the opposite direction here. Yeah, actually it starts to come down again there, doesn't it? That's sine.
I mean, hopefully, we all know that it's a nice swirly wave, and the point about sine is that it starts at the origin here and goes up to the left, to the right. Damn, don't know my left and right. Goes up this way. Lovely. And this is 1 here, and this is -1 here. So you see that the answers are always between plus and -1. Some people, when they try and remember what sine and cos are and whether they're positive or negative, use this graph, which is fine. You can do whatever you think is best. I find it easier from the unit circle, but not everyone does. Some people just remember this and mark out some of the useful points on it, and that's fine too if you feel that that's good for you. Cos, on the other hand, is exactly the same shape, but instead of starting here at the origin, cos starts going up over here at minus pi on 2. So it has exactly the same shape, but it does this here instead. They call cos an even function because if I flip it this way I get the same thing. Cos is an odd function because if I rotate it this way I get the same thing. So cos has a hump here at the origin and sine has its greatest slope here at the origin. That's sine and cos. And tan is a whole different story. Because tan has all sorts of weirdness going on at pi on 2. What happens at pi on 2 is that tan actually isn't defined. Because if you think about it as being the slope of that line, at pi on 2 it's a completely vertical line, it has no slope, technically it's got infinite slope. So what happens is you get this going on. Like that. And you'll see that the places where tan is undefined match with the places where cos crosses the x-axis. And the places where tan crosses the x-axis are the same places where sine crosses the x-axis. Now this is all lovely, and hopefully you've all seen these graphs at some point even before you did 1M. The issue is, now you keep being asked to see like sine of, 3 sine of 2x plus 5, and you're supposed to figure out what that looks like instead. And this is one of those points where it's really important to know a very important thing about how functions and their graphs work generally, because this same rule applies to all graphs of any kind, regardless of whether they represent functions or not. If there is a formula and there is a graph that goes with it, then if you change the formula in a certain way, it will change the graph in a certain way. And that's true for sine and cos and tan and x squared and anything. So if I was able to teach maths at school, if that was the only thing that I got my students to know, then I would be happy, because it's a really important thing to know. So, very important things to know are, if you have y equals f of x, then if you change the y's or you change the x's, what will happen is you'll change the y-axis and you'll change the x-axis on your graph. So this is just an example. So doing stuff to functions. It doesn't even matter if it's not even a function. You can have any formula at all and it should have a picture to go with it. So, suppose, just for argument's sake, my function looked like crap. What if it looked like this? Okay, this is not your trig thing. I want to point out that it works for any functions at all. And what if this happened at 1 and this happened at -1? And what if this happened at 1 here and this happened at -1 here as well? Just to show you what happens to my function. So this is my beautiful function. This bit here fits into this lovely box. Okay. So if you change things on the x to the x coordinate, you change the x-axis. So if I did this, x minus 3, I've replaced the x with an x minus 3. What will happen to my graph is it will move in the opposite direction on the x-axis. So it'll actually be over here instead. It'll be over here, which I really should have given myself much more space. Okay, so this used to happen at 0, well now it happens at 3. Okay, so changing the x, change the x-axis. Alright, so let's choose a... Subtracting 3 from the x meant I shifted plus 3 on the x-axis. Adding 3 to the x would mean I'd shift minus 3 on the x-axis instead. If I had this, y equals f of a half of x. So what I've done is I've divided the x by 2. What that'll do is it'll stretch out my x-axis by 2. So instead of what used to happen here at plus and minus 1, that'll stretch out to happen at plus and minus 2. But the height won't change. It'll be exactly the height it used to be. Okay, so dividing by 2 meant that I stretched it by timesing by 2 on the x-axis. And the same thing happens if you do stuff to the y. So if I did 2y equals f of x, which would be y equals a half of f of x, multiplying by 2 next to the y will shrink the y-axis. So multiply y by 2 means shrink by timesing a half on the y-axis. And same deal happens with adding stuff to the y and all of those things. Anything that you do to the y does the opposite to the y-axis. Anything you do to the x does the opposite to the x-axis. And you want to think about it as a process of which things have I done first. And each is done by replacing the x with something or replacing the y with something. And that happens to all functions of any kind, polynomials, sine, cos, exponentials, anything. Okay? There is one more thing that you could do. It's doing a minus next to the x. So that would be doing this. And that would flip it this way. So all your pluses would become minuses, all your minuses would become pluses. So what happened is I flipped this way. So minus the x means flip the x-axis this way, basically. And minusing the y means flip the y-axis the other way. Awesome. So, taking all that together, I can now, if I see a trig function, I can now actually figure out what it looks like. and I can work backwards from the picture of a trig function to figure out what happened to it. So your general trig function. So your general trig function, as an example, you might see something like I'd see something like that. 2 sine of pi t minus pi on 3 plus 4. And so what I've done is I've manipulated my x's and my y's to produce something or other. And I need to try and figure out what I did and in what order. So for me, it's easier to think about it this way. Other people think about doing stuff on the outside and doing stuff on the inside. I can't think that way. So I've just rearranged that. I've minus the 4 and then divided by the 2. So what I've done to my x, so this is what I do on my scribble paper. Right, to my t, sorry. So if I think about, I started with just sine t, and I progressively replaced the t with stuff. So if I had just started with sine t, first I could replace it by t minus pi on 3, and then I could replace the t with pi t. So t was replaced by t minus pi on 3, and then the t was replaced with pi t. So this move would shift it up by pi on 3 on the t-axis, and this move would actually shrink it inwards by dividing everything by pi. Oops, that's a minus, not an arrow. Okay, so that's telling me that what's happened is I've changed the places where it does all of its stuff to move it up by pi on 3, and then I've shrunk it down. Okay? And to my y, well, I've replaced my y with y minus 4, and then I've divided it by 2. No, crap, I haven't done that. Start with the outside and work my way in. I've first replaced my y with half of y, and then I've gone inwards one more step and replaced my y with y minus 4. So this move would shrink, would blow out, would grow my y-axis times 2, and this move would shift up 4. That's how I think about it. I know it takes ages, but I don't do it often enough to really need a really quick way of doing it. So you probably will also never do it that often. Need to empty my sharpener because it broke. So what happened to my graph then? So my original graph, so this is what sine normally looks like. And then I shifted it up by pi on 3. So this doesn't happen at 0 anymore. Now it happens at pi on 3. So everything that used to happen, that used to be 0, now everything's shifted up. It's now at pi on 3. So my x-axis has moved here. And I've also shrunk everything down by dividing it all by, sorry, that's not pi on 3. That's pi on 3. And I've shrunk everything else down by dividing it by pi. So this now happens at pi on 3. At 1 on 3, because I've divided by pi. Yay. And that's all good. And so this point over here was this plus pi. And now it's this plus 1, so it's 1 1/3. Lovely. And then on my y-axis, I grew my y-axis out by 2. So this used to be plus 1 and minus 1, and now it's plus 2 and minus 2. And then I shifted everything up by 4. So it's now not happening at minus 2 and 2, it's happening at everything up by 4. So my y-axis is actually all the way down here. Because this is actually 6 and 2. Yay! It doesn't seem easy, you see now, but that's the idea behind it. In an exam, they're much more likely to give you a function and say, what is it? So they'll give you this and say, what's happened to it? And you can go, well, I've shifted it up I've stretched it out. It should go from minus 1 to plus 1, and it actually the range there is 4, so it's really going, I've stretched it out by 2, and I've shifted it up by this, so there you go. If you want to talk more about it, because it's the sort of thing that makes it easier when you're talking to someone, come and visit the Maths Learning Centre and I'll chat it through with you, or one of the staff will. What's left? Trig identities. So, that's drawing graphs. Then there's these trig identities, right? And you're supposed to be able to convert one sine, cos and tan into some other things. And the thing I would really like you to know about trig identities is that there is a trig identities handout on the Maths Learning Centre webpage, and also they may have run out in the Maths Learning Centre. It looks like this. And this has all the trig identities I think you could possibly ever need. Not all of them are actually in your course. In particular, this one I just had half a page to fill, so I thought I'd put stuff in, because these are totally awesome, these ones. But you don't really need them per se. But all the other ones are sort of there. So let me show you. You've got sine and cos, they're your basics. Tan is sine divided by cos. That's your most basic trig identity. Sec is one over cos. Cosec is one over sine. Your lecturer probably writes it as just CSC. Cot is one over tan. And then there's this fundamental trig identity. Cos squared plus sine squared is 1. And that comes from your unit circle. Because it's a circle of radius 1, if you go the x-coordinate squared plus the y-coordinate squared, Pythagoras' theorem will tell you that it comes out as 1. So that's where this one comes from. But what you can do with this is you can divide everything by cos squared, and you'll get cos squared over cos squared is 1, sine squared over cos squared is tan squared, 1 over cos squared is sec squared, and you'll get this one, which is what this note here says. In the online version of this, you can actually go into the Layers tab in Acrobat Reader and turn off the annotations if you want to. So, in case they distract you. You can divide the original one by sine squared and get this one instead. I would say that the most useful ones in almost all of maths is these two. That one's not used as much. So, this is what I call the odd and even properties. Cos of minus x is the same as cos of x, no matter what x is. But sine, the minus will come out, and tan, the minus will come out. And that's called being an odd function and an even function. You may not have learned that in Maths 1M, but it will come back later if you do Maths 1A. And then there's the double angle formulas, which are quite important. And sine 2x is 2 sine x cos x. Cos 2x is cos squared minus sine squared. So you know how cos squared plus sine squared is 1? Well, cos squared minus sine squared is cos 2x. And what you can do with this one is if you replace the cos squared with a 1 minus sine squared, based on this one, then you can get that one, that one. And if you replace the sine squared with 1 minus cos squared, then you can get that one. They're called the double angle formulas. There are also what they call half angle formulas, which are not actually given to you in Maths 1M, but Ben Rawlack, one of the tutors, said I should put it in, and I agree with him. So if you've got sine of half of an angle, then that squared is a half of 1 minus cos. which you can get by rearranging these formulas and just dividing everything by 2. And then finally there's the sums and differences of angles. Cos of A plus B is cos A cos B minus sine A sine B. I'm long over being embarrassed by anything. At some point in the past I was embarrassed by saying this particular one, but I'm long over being embarrassed. I remember this by thinking that cos is antisocial and sine is friendly. Because you see that cos doesn't like sine, and so when you do the addition formula, it puts the coses with the coses and the sines with the sines. It's segregationist. Whereas sine is very friendly and likes to mix the sines and the coses, and has, when you do sines, you do sines with coses and coses with sines. And even worse, cos is even more unfriendly to sine because it puts the minus with the sines. There you go. That's how I remember it. Other people remember it by remembering complex numbers. So if you actually do this, Nicholas said I should tell you this. Oops. Nicholas said I should tell you this because it's awesome. Cis of A plus B in complex numbers, according to the rules of how cis works, that's cis of A times cis of B. And so you get cos of A plus B plus I times sine of A plus B. That's what cis means, cos I sine. Cos A plus I sine A, cos B plus I sine B. So this side I've just figured out what cis means. This side, cis for A means this, cis for B means this. And if you expand this out, you'll get cos A cos B plus I cos A sine B plus I sine A cos B plus I squared times sine A sine B, and I squared is minus 1. And look at this. The real bit, cos A plus B, is cos A cos B minus sine A sine B. That's totally awesome! The real bit says that cos of A plus B is cos A cos B minus sine A sine B. And the imaginary bit says that sine of A plus B is cos A sine B plus sine A cos B. Awesome, right? When I learned my trig identities, I did that, learned my trig identities in Year 12, and I didn't do complex numbers in Year 12, so I could never know the awesomeness that is this. And I also tend to have a personality approach to most things. With my periodic table, I think that the ones on this side are generous, and the ones on this side are greedy. And yeah, anyway, so I tend to have a personality approach to learning most things. But Nicholas said I should show you this because it's awesome. So yes, and then there is one more trig identity you need to know. This is just my unit circle stuff with the ASTC thing, and this is cos of pi on 2 minus x is sine of x. That's really important to know. And these ones, well, they're awesome because this is what happens when you add pi on 2. And look at this. If you add pi on 2 next to the x, cos becomes minus sine becomes minus cos. These are the derivatives. Isn't that awesome? Adding pi on 2 differentiates it. Wow! Anyway, I just think it's cool. So, there are two parts to trig identities, and you should remember to yourself that there are two things you could be asked about a trig identity. You could be asked to verify it, or you could be asked to prove it. So, Verify means sub it in and see if it works. So as an example, verify cos 2x equals cos x squared minus sine x squared for x equals pi on 2, for example. So that question just says, sub in the pi on 2, see if it works. Figure out each side separately though. So cos of 2 times pi on 2 is cos of pi, because 2 times pi on 2 is pi, which is, according to my unit circle, pi is there, x coordinate is minus 1. Okay? Cos pi on 2 squared minus sine pi on 2 squared. Now cos pi on 2 is 0, and sine pi on 2 is 1. Verified. Done. That's it. Therefore, formula is true. For x equals pi on 2. That's what verify means. Verify, the actual word means establish the truth of. And that's what I've done. That's what verify means. But to prove that something is true, you would have to start with one and end with the other with steps in between. Means you use algebra to get from one to the other. In general, if you're asked to prove, you'll be asked to prove some fancy trig identity, and what you'll do is you'll use the fundamental trig identity somewhere. Because you're never asked to prove the fundamental trig identity because you say, well, look, it's the unit circle. So yeah, an example of that would be something... just trying to think of one. E.g. prove that, let's see. Give me 1 second. Sec theta squared plus cosec theta squared equals tan theta plus cot theta squared. There's this weird bit, in the fuzzy bit on the document camera. So to prove that, what I would need to do is I would need to start with one, do working to produce the other. So whichever one seemed like the best one to start with. Alternatively, you could start with one and do stuff, and start with something else and do stuff, and prove that they come to the same place. That will work too. So I think I might start with this one for no good reason, because they both look hard to me. Normally what you do is you start with the most complex one and try and make it look simpler, because simplifying is easier than complexifying. So tan theta plus cot theta squared. So tan theta would be sine, well, I'm just going to expand it out, see what I get. Tan theta squared plus 2 tan theta cot theta plus cot theta squared. Awesome. Right, now, tan theta squared is in a trig identity. It's in the one with sine and cos, and you divide it by, and you'll get 1, just a second. This one, 1 plus tan squared is sec squared. Okay, so tan squared would be sec squared minus 1. Okay, so this is sec theta squared minus 1. That bit there. The next bit, well, cot theta is 1 over tan times 1 over tan theta. Cool. And cot squared, there was a trig identity with that as well. Cosec squared minus 1. Cool. And then if we expand that out, we get sec theta squared minus 1 plus, and they cancel, so plus 2, plus cosec theta squared minus 1, and they all cancel, so I get sec theta squared plus cosec theta squared. Yay! It's true, because I started at one, did working, and got to the other one. There was a famous one in one of the tutes or something where you ended up with a 1 minus cos theta on the bottom. What you need to do is times by 1 plus cos theta on the top and bottom, and you'll be able to use your trig identities to make that go away. But this one's particularly straightforward because it uses the trig identities. What would have happened if I was actually doing this in the exam is over on the side here, or possibly on my scribble paper, I would have gone, just crap, I don't know the one that goes with tan squared, so I would write. And then I divide it by cos so that I could remember what this one was. And I divide that one by, crap. I divide that one by sine. So I would have written this somewhere on my page so that I could remember these things here. So that gave me that one, and that gave me that one. Right. Actually, this is a truly awesome trig identity because of where it is in the unit circle. And if you want to know more about it, I'll tell you, because I only discovered it this morning, and it's so cool. That's it, everything I have to say about trig identity, trig functions, unless you have something to ask. So feel free to ask something or not. Okay? I think that's everything that was in the trig functions. I can't guarantee that it is because I wasn't there. But I think that's everything. If you have anything else to ask about, that's what the Maths Learning Centre is for. So feel free to drop in and we'll chat about it. I'm going to stop my recording for a second so that I can start on the polynomials.